Have you ever looked at a giant cargo ship and wondered, how in the heck does that thing even float? It's a fair question, and the answer lies in a fascinating field called naval architecture. These are the men and women who design, build, and maintain the ships that keep our world moving. Now, I'm not talking about fancy yachts for the rich and famous, I'm talking about the workhorses of the sea tankers hauling oil, container ships carrying everything from TVs to sneakers, and even massive cruise ships that are basically floating cities. These vessels are engineering marvels, and it all starts with understanding two fundamental principles: stability and hull design. Think of it like this. A ship is like a giant bathtub toy. You want it to float, right? But you also want it to float upright and not tip over. That's where stability comes in. And just like bathtub toys come in all shapes and sizes, so do ships. The shape of a ship's hull, or its body, plays a huge role in how it moves through the water. So, buckle up, because we're about to dive deep into the world of naval architecture. We'll explore the forces that keep ships afloat, the different types of hull designs, and how these principles are applied in the real world. By the end, you'll have a whole new appreciation for the ingenuity behind these floating fortresses. Let's start with the basics. How do ships stay afloat? It all comes down to a delicate balance between weight and buoyancy. Think of a rubber duck in a bathtub. The duck floats because the water it displaces weighs more than the duck itself. That upward force of the water is called buoyancy. Ships work the same way, only on a much larger scale. A ship's weight is spread out over its hull, and the water it displaces pushes back up with an equal force, keeping it afloat. This is where the concept of the center of gravity comes in. Just like with that rubber duck, if the center of gravity is too high, the ship becomes unstable and could capsize. That's why naval architects spend countless hours calculating the weight distribution of a ship, from the cargo it carries to the fuel in its tanks. They have to make sure that the center of gravity stays low enough to keep the ship stable, even in rough seas. It's a delicate balancing act, but it's crucial for the safety and stability of the vessel. Now let's talk about hull design. It's not just about making a ship look sleek and stylish, it's about optimizing its performance for its intended purpose. Think of a cargo ship versus a speedboat. They have very different jobs to do, and their hull designs reflect that. Cargo ships, for example, are all about maximizing cargo capacity. They have wide, boxy hulls that allow them to carry massive amounts of containers or bulk goods. Speedboats, on the other hand, are built for, well, speed. They have sleek, narrow hulls that slice through the water with minimal resistance. And then you have specialized vessels like icebreakers, which have reinforced hulls designed to break through thick ice, and submarines, which can adjust their buoyancy to dive and resurface. The point is, hull design is all about finding the perfect balance between stability, speed, and cargo capacity for a particular type of ship. Real-world applications, from cargo ships to cruise ships. So, how do these principles of naval architecture play out in the real world? Let's take a look at some examples. Imagine a massive container ship loaded with thousands of shipping containers. The weight distribution of those containers is crucial for the ship's stability. Too much weight on one side could cause the ship to list, making it difficult to navigate and potentially dangerous. Now picture a luxury cruise ship. These floating resorts are designed for comfort and stability, even in rough seas. They often have stabilizers underwater fins that counteract the rolling motion of the waves. It's all about keeping those passengers happy and their martinis from spilling. And let's not forget about submarines, the stealthy ninjas of the sea. These vessels can adjust their buoyancy to control their depth. They use ballast tanks, compartments that can be filled with water or air, to sink or rise in the water column. It's a delicate dance of pressure and buoyancy that allows them to operate underwater. The weight of the matter: ballast and stability. Remember that delicate balance we talked about earlier? Well, sometimes ships need a little help to maintain that balance. That's where ballast comes in. Ballast is simply heavy material like water or rocks that can be added to a ship to improve its stability. Think of it like adding weights to the bottom of that rubber duck. By strategically adding or removing ballast, naval architects can adjust a ship's center of gravity, ensuring that it stays upright and stable. This is especially important for ships that carry varying loads like cargo ships or tankers. Ballast also plays a crucial role in compensating for the weight of fuel and water as they're consumed during a voyage. By adjusting the amount of ballast, the crew can ensure that the ship remains balanced and doesn't become top-heavy. It's all about maintaining that delicate equilibrium between weight and buoyancy.